Hi folks, we're going to take a look at 7A from part A of the Unit 3 assignment. So they want us to find the points of inflection of this function here. So in other words, we're going to be working with the second derivative. Now just a quick comment about this function here in terms of finding the derivative. One thing I could do to simplify my life is to apply the ski-slope rule to the numerator and write this as 2 ln w. Now, the reason why I'm not going to do that is that if I rewrite this as 2 ln w over w, I look at the domain of this function, I see that w can only be greater than 0, whereas if I keep the w squared, the domain now can become everything other than 0. And so it means I have to worry about figuring out what happens on that other side of the domain. So the easiest thing to do is to just deal with it as it is. The derivative will be a little more complicated, but just means I don't have to worry about any other missing values that won't cut them out of my work. All right, so step number one is we'll find the first derivative. Okay, derivative of the numerator, so I have to apply the chain rule. So derivative ln w is ln w squared is 1 over w squared times the derivative of w squared, which is 2w. Okay, then I multiply that by the denominator function minus, so the numerator function ln w squared times the derivative of the denominator. Derivative of w is just 1, so nothing else there, and all over the square of the denominator function. Okay, so before I take the second derivative, obviously I'm going to simplify here, and lots of nice things happen because here this w squared is going to reduce with the two factors of w in the numerator. So I'm left with 2 minus ln w squared over w squared. All right, and this now is much easier to take the derivative of, so now we'll find the second derivative. Okay, so derivative of the numerator, so again 2 is just a constant, so the derivative is 0, and here I have this negative 1, which is just a constant, times the derivative of ln w squared, which I already found earlier. Okay, so I'll write it out again, 1 over w squared, okay, times the derivative of w squared, which is 2w, okay, all this times the denominator function, w squared, minus the numerator function, 2 minus ln w squared, times the derivative of the denominator, which is 2w. Okay, all over the square of the denominator function here, so that's going to be w to the 4. Okay, so before I determine where the points of inflection are, so I'm going to solve for when the first derivative is equal to 0. I'm not going to bother where it doesn't exist, because it doesn't exist when the denominator is 0, in other words, where w is 0, but w equals 0 is not even in the domain, so it can't be a point of inflection. So I'm just solving for where the second derivative, sorry, this is the second derivative, where that's equal to 0. Okay, so let's simplify here. So I have a w squared and w squared, which cancel out. Okay, so let's work with the numerator here. So I've got common factors here because I've got a 2w and another 2w. So I'll take those out. And what are we left with here? Well, the only thing we're left with is negative 1. All right. And then here I'm just left with minus 2 and then plus ln w squared. Okay. And now I can reduce this w with one of the w's in the denominator. So I'm just left with solving 0 equals, so what do we have, 2 times, and here we're left with negative 3 plus ln w squared all over w cubed. So since this is a fraction, I just have to solve for where the numerator is equal to 0. So that's going to be whatever's in this bracket. So here we have negative 3 plus ln w squared has to be equal to 0. So ln w squared is going to be equal to 3. And I'm going to take the exponential function base e of both sides. So that is just going to be e to the ln w squared is just going to be w squared equals e cubed. And now finally I can solve for w. So w is equal to positive or negative. Remember, I'm taking the square root here. So square root of e cubed, or I can write it as positive or negative e to the 3 over 2. Which I think is going to make it easier to actually find my y values. Now, all we've done is determine the w values that make the second derivative equal to 0. I still haven't proven that these correspond to points of inflection. I have to check the sign of the second derivative. Okay, so I'll do that here. Now, I still have my 0, which is where the second derivative doesn't exist. So I want to make sure I include that in my number line, because while it can't be a point of inflection, the sign of the second derivative can change there. And the other 2 points are, and since I need to actually stick in some values, I'm going to estimate these numbers here. Okay, so let's do e to the 3 over 2. Okay, and that's about 4.5. So we'll have 4.5 here, and we'll have negative 4.5 on that side. And now we just have to determine the sign of the second derivative. All right, so here we have the w cubed, so make sure you're careful with this here, because this will be affected by the sign of the input. Okay, and obviously the 2 is always positive. All right, so let's put in negative 5. Okay, and let's see what happens when I put in negative 5. So I have ln of negative 5 squared, so I have ln of 25. Okay, and then minus 3. So positive in the numerator, okay, but negative in the denominator, because negative 5 cubed is negative. So I have negative here. Now let's put in, say, negative 1. Okay, so again, ln of negative 1 squared is just ln of 1, which is 0. Minus 3 is negative 3. Over negative 1 squared is negative, so negative over negative is positive. Okay, so that means we have a point of inflection at negative e to the 3 halves. All right, so now let's put in positive 1. So again, ln of 1 squared, that's 0, minus 3 is negative, over a positive number, because 1 cubed is positive. So here we have negative again, and then let's put in 5. So here we have ln of 5 squared, which is 25, okay, minus 3, which is positive, over 5 cubed, which is also positive. So the whole thing is positive. So again, we have a change in concavity. So we also have a point of inflection at e to the 3 halves. All right. Now, since they technically asked us for the points of inflection, we should be finding the y values. Okay, so let's go back to the original function, ln w squared over w. So we'll write this out here. All right, so let's put in e to the 3 halves. So f at e to the 3 halves, okay, is equal to ln of e to the 3 halves squared over e to the 3 halves. Okay, here I multiply by my exponent rule, so that's just going to cancel out. So ln of e cubed is just 3 over e to the 3 halves. Okay, for f at negative e to the 3 halves, I'm going to have something almost identical, because the numerator is going to do the exact same thing, because here we have ln of negative e to the 3 halves squared. Okay, but remember, the square also applies to the negative there. So maybe this one here, I'll write it out. Whoops, over negative e to the 3 halves. Okay, in the denominator. So here we have ln of, remember, square negative number becomes positive. So this just becomes e cubed again, and negative e to the 3 halves. And again, that's just equal to 3. So we end up with negative 3 e to the 3 halves. Okay, so what are my points of inflection? They are e to the 3 over 2, and its y value 3 over e to the 3 over 2. Okay, and our second one is going to be negative e to the 3 over 2, and negative 3 over e to the 3 over 2. Okay, so lots of arithmetic in this one here, but in the end, let's just recap. Okay, what we actually had to establish is, since we were looking for points of inflection, we were looking for where the second derivative was equal to 0, and then all this, and then we had to show that the sign of the second derivative changed. In other words, there was a change in concavity to confirm that they were indeed points of inflection. And all this other stuff is just arithmetic. It's just an exercise in knowing your exponent rules and exponential and logarithmic expressions. Okay, that's it for this one.